Okay, so today we're going to see the introduction to ME171 and the different methods of modeling and simulation. So in here we go, and we have just a few elements and devices that are systems in here in the different domains. And we will look at an example of a simple system so that we understand the idea of how the a model of reality can be put into the computer. So this is the process that we will be using for doing this representation of reality. We start with a physical system. We go to a schematic model or a little drawing of what our system is like and the different elements that it has. Then somehow we need to get the differential equations. This is the point where different methods do different things. Either you know how to derive these equations, or you have the computer do it for you. You have to make a decision. At that point, the decision is that to use the either the block diagram method or use the bone graph method. Whichever way you do it, you're going to you're going to look for a simulation language that would allow you to interpret the results. Not only interpret, though, actually perform the calculations. The simulation language in our case, in our class, is MATLAB and Simulink. Um, we can do these different things, like I told you, by hand, or we can do it using the computer. This step where you go from a schematic model to the mathematical representation is what CAMG does. CAMG is a software package. CAMG stands for Computer Aided Modeling Program with Graphical Input. So once you have that, either, like I said, by hand or automatic, on the simulation language, you will be able to interpret the graphs or the numerical results, and then you will be able to go back and change your system and do the design. That's in general the idea. So in here, what we're going to do is we have a simple system, like a simple suspension system, where you have a mass, and of course you have spring, and you have the damper, and you have the input from the ground here. We will take first the approach of writing the equations by hand. So what do we have to do to make a mathematical representation of the system here? Several things that I would like to address before we do that. I have made it color coded in here in such a way that you recognize that the massing here is this inertia element. Both are represented here and written in red. The green element in here is the damper here. A damper is an element that actually dissipates energy, so it's a resistive element, and we are going to call it the R element. This we're going to call it the I element. And this one, which is the one that stores potential energy for a spring, this is going to be the compliance element, or we will call it the C element in here. Yeah? So what we have is we have the physical system, and now we have a way to represent it in a mathematical way. How do we actually do that? We do that by going to the mass and doing a free body diagram on the system in such a way that We write all the forces in there, and then we apply the very basic principle that is very basic principle using Newton's equations, Newton's law, that says that the summation of the forces acting on a particle is actually equal to the rate of change of momentum. So in other words, we apply forces and the particle moves. Therefore, the summation of the forces equals to the rate of change of momentum, which is mass times acceleration is another way of saying that. This is, see here's rate of change of momentum. Momentum is defined as the product of the mass times the velocity. So in here we have the summation of the forces and produces this differential equation. Now, what I would say is this is the time where you're going to be using those differential equations that you learn in your introductory math courses. So you see in here the differential equation reveals that you have the mass inertia element, the red one over here. You see the influence of the resistive element here and the influence of the spring element or compliance element. And of course, in this case, mg is the source because it is the source from the ground. One way of doing this is to represent this differential equation into a block diagram. Yeah. I think if you look at the equation here and then you look over here, this may appear overwhelming to you right now because there's no system. You know, I can tell you that the block diagram represents this equation, but unless we develop it ourselves, slowly, step by step, this may not much make more sense to you right now. The point I'm trying to make in here is that this is the method that goes from the mathematical representation of the system to this block diagram where you can actually put it into the Simulink software. Okay? So I think that these symbols are very well understood to Simulink, and once you put them in here, you can do the simulation. We're going to be doing that in a little bit, but in here you see another alternative that you can do is represent this block diagram into a computer program that you yourself can program or go into a simulation language that would allow you to solve the equations. So nevertheless, all this block diagram method, it is together with this representation in the graphical form and with the solution in the code form. It can't go the other way. Either you have some sort of a software that allow you to solve the graph itself like it is, which is software like Simulink, or you actually do a little program. But what I'm trying to tell you is there is another way of doing that, and that is to make the computer do this. And that's where the bone graft model comes into picture. The bone graft modeling technique comes into picture. That bone graft model, it is in here. And just at, just as at this point, it is my responsibility to show you how do you actually get this, as well how you actually get this. All I'm trying to say to you is either you can go this way or you can go this way. Okay? So what I would like to do is let's just go to my OneNote and we will work it out this way, and we will work it out this other way. Okay, so we're going to go back to the OneNote over here and do that. So for the moment, okay, so let's just take a look on how we are going to do this. To do that, let me go to my note in here where I have the representation of the system like that. And we are going to just wrestle with this both in the block diagram form as well as in the um, in the in the bond graph form. So in here, what I would do is you have this. We're gonna let's just put it in with another color. We see this is your forcing here. This element we are going to call it a source of effort here. Yeah, and this is going to be my inertia element in here. This we're going to call it, this of course is your mass in here. What I'm going to do also is in here I'm going to use the symbol to represent the velocity of this mass. So velocity that is going this way like this. In here you have a, we're going to call this source of flow. With velocity equals to 0. So this is the wall that I have in here, okay? Okay. And this is going to be my C element, which is obviously this spring in here. Yeah. And then this is my R element, which is the damper. See, I can write really well as if I write it on the board now. So what I'm going to do is I am going to show you how to represent the system with with this method where we are going to put just a symbol here. This is going to be the symbol for the velocity. We will put the symbol for the force in here. So this is SE with value F. We will have a C element in here, which has a value 1 over K for the spring. We will have an R element, which value B, like coefficient here. This C is 1 over K here. This is the value, B here. And then we have again another reference velocity with velocity equals to 0. And we have in here the wall. Okay, so you see I have laid out the elements that my system is made of, but right now they don't make any sense because they are not connected together. But what I would like to do now is I go and say, okay, really the source is the one that originates this velocity, and power goes from the source into the system. In here, I missed writing the mass in here. I didn't do that. So let me put in here M. And so what I'm saying is that this velocity is common to the mass as well as to this force. And in here you have the this this is connected here, see? But you see between the wall, this wall over here, between the wall and the and this other system here, between the mass, we have these two elements. So to represent that, we use the zero junction that allowed us to make the difference between x dot and the velocity of the wall.
That's 15 minutes.
Yeah, and this is another one which is x dot minus velocity of the wall. And both of these elements see that difference. This, you see, we have laid out some way to um, to indicate all these elements in here connected with the different um, elements. You see, the source is connected to the mass. The mass, of course, has this velocity x dot, and between this and the other, and the wall, we have a difference, x dot minus the velocity of the wall, and that is seen by the C and the R. This representation is called a bond graph, or I would say called, we could call it junction graph or connection graph. How is that better?
So what do the dots represent?
Huh?
What do the dots represent?
What dots?
Like on all of the symbols, like
The two little dots?
yeah.
I say it's just a way of saying this is the value of what that element is. Like, for example, the element is called source of effort, but the value of that is F. The I element is, the value of the I element is the value of the mass. The value of the damper is the value B. The value of the C is 1 over K. That's what that means.
Okay.
Just a way to do that. So what happens is that the computer now, this is in a way that is ready for us to is in a way that is ready to enter it into the computer. And I'm going to show you how that works. Now we have to use another piece of software. So in here we go, and we say, we go to the KMG software, which you will find it here, right there. And then go to this. Computer is going to run this software, and what you're going to do is you're going to do is use this program. We're gonna call it new, and then I can bring in the bond graph model that I have in there. So in here you have this, and we could move it down here so that you can, how do we do this? Okay. We will bring it to be small over here. This is the stuff that I cannot do if I use just the whiteboard. So in here, I just want this picture, right? So what I'm gonna do is we're gonna put that picture close in here, and then we'll use the software. Mhm. Somehow I'm having a little bit of a difficulty here. Yeah, there we go. So in here, I could put this element in here, and you will see that it is pretty easy. You could just draw it like this, and then you have the I element over here. Yeah, remember it is the 0 was in here, and then we had another one element over here like this, and then we had the C element like this, and then you had the R element over here, and then you had the SF element over here. This is we have translated our representation in a graphical form to the computer. And now what we're going to do is we're going to say, hey, just go to the MATLAB software. The computer is going to derive the differential equations of the system, and we have given it something like this, the model, and then now it will actually go to MATLAB. So the two programs, please enter the code. Okay, they talk with each other, and then you have a MATLAB directly already programmed in MATLAB. So it delivers your model to MATLAB. Okay, so we will just wait a little bit between the two programs. They do a handshake, and once they do, we should be able to see the the we should be able to see MATLAB ready to do the simulation of this little system. Of course, to be able to do that, we really need some values. Uh-huh. Right now, MATLAB is taking longer than it should. But we are going to, there you go. You know what it did? MATLAB created, ChemG created some MATLAB files that MATLAB can actually use to do the simulation. And the way we're going to do that is to enter some values for the force, values for the mass, values for the C element, and values for the R element. MATLAB is a little bit slower than usual. There we go. So I very briefly, it will take us only about a couple of minutes. We go and enter the values of those. Like, for example, we do the I1, the C. I have some numbers that produce some reasonable pictures. And the source of this, we're gonna do a 10. It's a source. And then, of course, the value of the, the volt, we said is 0. We're gonna simulate this from 0 time, and you're gonna give it like 5 seconds. And then, if you actually run this thing, you would get a file. Well, right now we got an error in here, line 22, it says, obviously because we didn't enter the initial conditions, which we need to give the initial conditions, system is not moving. So, and if you run this, the computer is going to come back and it will do a simulation for you. See, I gave it an input in here and it gave me the answer. Okay, we'll stop here and we'll look it up at the other method in the next